Broadly broken down into three main parts: classical physics, quantum physics, and relativity. We'll start with classical physics, and a good person to start with is Isaac Newton. His laws of motion describe how everything made of matter moves about, and his law of universal gravitation tied together the motion of planets in the sky with the falling of objects on Earth into one elegant and general description. He also invented calculus, a supremely powerful mathematical tool which has been used over the centuries to drive new physics. Calculus is really a part of mathematics, but physics and mathematics are inseparable. Maths is the language of physics, and you can imagine it like the bedrock that the world of physics is built from. Newton also made strides in the field of optics, which is the physics of light and how it travels through different materials. It explains refraction seen in prisms and lenses, which are used to focus light in telescopes, microscopes, and cameras. Telescopes enabled us to peer into the depths of space and observe the wild array of objects there, and developed astrophysics and cosmology. Optics is closely related to the theory of waves, which is basically how energy can travel through disturbances of a medium, like ripples on the surface of a pond or sound through the air. Light doesn't need a medium to travel through. It can travel through the vacuum of space, but it still follows the same principles as all waves, namely reflection, refraction, and diffraction. This leads us to electromagnetism, the description of magnets, electricity, or more generally, electric and magnetic fields. It was a physicist called James Clerk Maxwell who discovered that these are two aspects of the same thing and derived the wonderfully elegant rules of electromagnetism and theorized that light was an electromagnetic wave. Electromagnetism also explains all of electricity. Jumping back a little bit, classical mechanics is related to Newton's laws and covers the properties and motion of solid objects, how they move when forces hit them, and what happens when they are joined together, like in gears or in buildings or bridges. Fluid mechanics is the description of flows of liquids and gases. Using fluid mechanics, you can work out how much lift is generated from an aeroplane's wing or how aerodynamic a car is. Fluid mechanics is notoriously difficult, mostly because the motions of tiny things like molecules get really complicated really fast, which leads us to chaos theory. Chaos theory is the description of large, complex systems and how small differences in initial conditions can lead to very different final outcomes. Thermodynamics is the description of energy and how it passes from one form to another. It also includes entropy, which is a measure of order and disorder and basically tells you how useful different kinds of energy are. Energy is a fundamental property to physics, and although I've written energy here, I should have written it everywhere on this map, because everything has energy. So that's all of classical physics, the picture of the universe we had around the year 1900. It told us we lived in a universe where everything ran sort of like clockwork. If you could measure everything accurately enough, the future was kind of predetermined. However, not everything was solved. There were just a few holes in experiments that hinted at something more. The orbit of Mercury was slightly too fast, and some strange things happened on the smallest scales with electrons and light, which were all unexplained. Physicists at the time thought that they'd solve and explain these problems soon enough, but poking at them, they unravelled the new domains of relativity and quantum physics and turned our understanding of the universe completely on its head. Albert Einstein was the genius who developed the theories of special and general relativity. Special relativity predicts that the speed of light is constant for all observers, which means that when you travel really fast, weird stuff starts happening, like time slowing down. It also states that energy and matter are different aspects of the same thing, through the famous formula E=mc². General relativity says that space and time are part of the same fabric, called spacetime, and that the force of gravity comes from objects bending spacetime, making other objects fall in towards them. While relativity describes the very big, other physicists were busy at work on the very small in the world of quantum physics. Atomic theory probed the nature of the atom, and more detailed descriptions of the atom were developed, from a tiny sphere to electron orbits, to energy levels, and then to the electrons being wave-like charge distributions. Condensed matter physics describes the quantum physics of many atoms together in solids and liquids, and is where many great technologies have come from, like computers, lasers, and quantum information science. Nuclear physics describes how the nucleus of atoms behave and explains radiation, nuclear fission, the splitting of an atom used in our nuclear power plants, and nuclear fusion, which takes place in the Sun and will hopefully soon be harnessed here on Earth. Particle physics probes even deeper to find the fundamental subatomic particles that everything is made of, and are described in the Standard Model of Particle Physics. And quantum field theory captures all of quantum physics and combines it with the special theory of relativity, and it's the best description of the universe we have. Unfortunately, quantum field theory doesn't include gravity, and so physicists don't know how to join together quantum physics and the general theory of relativity, leading to the giant chasm of ignorance. One day in the future we hope to close this chasm and come up with a theory of all of physics. We call it quantum gravity, and there are many attempts to do this. Some examples are string theory or loop quantum gravity, and there's many more. But quantum gravity isn't the only thing we observe but don't understand. There are also the major puzzles of dark energy and dark matter, which seem to make up 95% of the universe, so all of our physics only really describes 5% of what we know about, and everything else at the moment is a mystery. And there are many other mysteries out there, like the Big Bang, and no doubt there's things beyond that we don't even know that we don't know. Which gets to the lofty cloud which floats over all of physics, philosophy. Although many physicists make fun of philosophy, it's the big philosophical questions that motivate a lot of physics, like what is the fundamental nature of reality? How come the universe even exists? Do we have free will if we're just made of physics? Well, how do we know that the way that we do physics and science actually gets to the fundamental truth of the universe? And just why is all of physics like the way it is? Well, those are rather big questions, ones which we may or may never answer, but there's no reason to give up trying. After all, physicists are not quitters. And that was the map of physics. So that's the end. Thanks for watching the video. I hope you enjoyed it. I'm still kind of working on the format of this channel, playing around with a few different things, and I kind of like this animation style. So let me know in the comments if you enjoy this kind of stuff, you want me to do more, and if there's any specific subjects you want me to cover. I'm totally open to ideas. I've got a whole bunch of videos that are coming down the pipe, so keep your eyes peeled for those. So until next time, see ya.